Hi class, I promise you that I will give you extra recorded lecture on PDE. Okay, so I'm going to give a summarize over this topic, the rest of the several equations. Okay, partial differential equations. So if in previous notes there are several PDEs that are very well known in physics. Okay, if you look back at my introductions of the topic. However, the key concept to solve can be summarized as below. Okay. First, actually, it is related to the eigenvalue and eigenfunctions. So in particular, it's related to eigenvalue equations when you are solving the differential equations. So the idea is motivated by the vibrating string. So let's look at this second order. So over here is second order differential equation. Okay, because of the y prime, y double prime, so this is equivalent to dy over dx squared. And then you have some, look at lambda there, some coefficients lambda. Lambda y equals to 0. It's a linear second order differential equation. So if you want to do this, let's say if you're adding some boundary value conditions, so you have this differential equation satisfy conditions such as y0 equals to 0, and you have another one is y pi equals to pi. So you have a initial condition here. Okay, now look at the situation. So usually we're going to look at the situation with boundary conditions and analyze further. And there are three types of the conditions, which is lambda less than 0, so very small lambda, negative lambda, and then you have lambda equals to 0, and then you have lambda larger than 0. And this is ideal just to find what lambda is. Okay, and usually if you look at this part, this is very what we call trivial solutions, and usually we don't want that. Okay, and most probably usually we're going to look at lambda much more larger than 0. Okay, so why this is I call eigenvalue equation. So we look back at equation 1. Okay, so for convenient, okay, I teach you previously how to solving your differential equation. At least you're getting the general solutions by finding the roots. Okay, so for convenient, let d stand for d dx. Okay, so let's define this. Okay, so if you put d equals to dx, so if you have dy, okay, look at this dy, so dy is putting d dxy, and this is nothing more than equal to y prime. So if you have d square y, so this is like y double prime, so it's a second order derivative. So you can try to find the roots. Okay, how? Okay, so now you, let's say from equation 1 here, okay, you substitute d square plus lambda and then multiply by y equals to 0, and you know that your y definitely cannot be 0 because your y is the solutions to your differential equation. So what's left, if this is correct, this must be true. Okay, same thing that you learn a standard procedure. So then you have d square equals to minus lambda, and then your d eventually is plus minus I square root lambda, and this gives you a complex roots, and you can find the general solution having either in terms of exponential form or in terms of a linear combinations of sine and cosine functions. And look over here, this is the multiplications of your sine coming from the lambda, and then you can apply the boundary conditions as usual, whether you are with the initial conditions y0 0, and you're getting your y, and then you want your y pi equals to 0, and then finally you determine what lambda is, and eventually you get the solutions in terms of your n pi x. So your y something like sine, you get your n pi x, right? Okay, and then eventually you can list down all the solutions of okay, up to n, and these are just called the eigenvectors. Okay, so that is the rules to solve some differential equations. Okay, not yet PDE, but it's related to the eigenvalue equations and finding the eigenvectors, which are the solutions. So these are also the solutions. Why? Okay, now let's look at the diffusions or heat flow equations. Okay, so I start with given by equation number 1. Okay, so you have a Laplace operator here. Okay, Laplacians of function u, and then you have 1 over alpha square. So alpha square is a constant. This is definitions given. Constant characteristic of the material. Alright, through which your heat flow. Okay, so if we have this now, it's really PDE. Okay, second order PDE, and we always assume the solutions. Okay, u is a multiplications of two function. So you have functions of t, okay, of variables t. So this is function number 2, and then you have function number 1, f. So in this case, we stick to either f respect to x, y, z, the Cartesian, multiply with function t. Okay, remember this is not a temperature, it's just notations for t as another function with respect to time. So if we assume this as a solution, so usually we substitute equation 1 in equation 2. Okay, and look carefully. Let's say if you take one part of this, okay, so it really means that you are putting your f, but you are, because it's only related to t, so you are trying to do derivative of functions t over time, over small t. Okay, I call small t, right? But this is the thing after you substitute. Okay, you just substitute u inside, and right hand side, left hand side, and also right hand side, and look carefully over here. So my left hand side, you have a functions of f of 3 variable, and then you have a functions of t of 1 variable. Now over here you also have u equivalent to u, but u here is, I just drop down the 1 in the bracket. Okay, so this really means that you have f x y z, and then you have t equals to time t. Okay, so what is the so now you see that on the left hand side I keep the variables in it, but the right hand side I just remove them for simplicity. Then what you should do is you rearrange, okay, accordingly. You separate the variables. Okay, this is something that is very common. Separate the variables. Alright, so once you separate the variable, okay, looks what I did over here. You put everything f to your right hand side. These are all f, and another one, these are all functions of t. Okay, so once you do that, if this is true, we take both sides are the same constant, and usually we apply one part. So this is number 1 and this is number 2. So the first one is you choose as a minus signs, okay, because there is some common separation constant to be a minus signs. Okay, but you can also have a separation constant in terms of plus, but it gives you a different general solution. Okay, so in this case we choose minus signs k square. Okay, k square over here because you want to maintain not having a square root inside this. Usually previously you have lambda x. Okay, I don't want to have a square root there, so I make it square. Alright, okay, and then so once you do this, so you just solve. So looks over here all are ODE. Okay, so you're finding the solution. You're finding the solutions of finding the roots. Okay, so this is just one of the solutions. So next you look at dt and dt. So this is k square alpha square t. So what you should do, again separate the variables t, and then you have minus k square alpha 2 dt. Okay, so you integrate both sides, so you have ln t and then you have negative k square alpha 2t, and then your t is become exponential k square alpha square t. Okay, alright, that's all. Thank you. We're going to continue next.